Hello friends, welcome to my lecture on stability of linear systems. We begin with an example on a system of linear system dx by dt equal to 2x minus 7 by dy by dt equal to 3x minus 8y. Here if a is equal to 2, b is equal to minus 7, c is equal to 3 and d is equal to minus 8. So, the characteristic equation is lambda square minus a plus d into lambda plus ad minus bc is equal to 0. When we put the values of a, b, c, d here, okay, what we get? Lambda square minus a plus d. So, 2 minus 8 means minus 6. So, we get lambda square plus 6x, and then ad is minus 16, and then we have vc is equal to minus 21. So, plus 21 equal to 0. So, we get lambda square plus 6x plus 5 equal to 0. The factors here are lambda plus 5 and lambda plus 1. So, the eigenvalues are lambda equal to minus 5 and lambda equal to minus 1. Thus, we can see that the roots of the equation are the roots of the characteristic equation are real, unequal, and they are of the same sign, and therefore, by the case 1 which we have considered in the previous lecture, the critical point 0 0 here is a node and it is asymptotically stable. Now, let us go to the case 2 where we will consider the case where lambda 1 and lambda 2 are real, unequal, and are of opposite signs. So, let us say the root lambda 1 and lambda 2 of the characteristic equation lambda square minus a plus d into lambda plus ad minus bc equal to 0 are real, unequal, and of opposite signs. So, then the critical point 0 0 of the linear system we shall see is a saddle point. Now, let us see how we get a saddle point here. Suppose lambda 1 is less than 0 and lambda 2 is greater than 0. So, that means lambda 1 is negative and lambda 2 is positive. This we do for definiteness. Now, the general solution of the system 1, here is then given by x equal to c1 a1 e to the power lambda 1 t plus c2 a2 e to the power lambda 2 t and by equal to c1 b1 e to the power lambda 1 t plus c2 b2 e to the power lambda 2 t, and a1 b1 a2 b2 are definite constants and satisfy the condition that a1 b2 is not equal to a2 b1. c1 c2 are arbitrary constants. Now, we will analyze the situation here as we analyzed in the case 1. Okay. So, choosing c2 equal to 0, what we obtain? We obtain x equal to c1 a1 e to the power lambda 1 t by equal to c1 b1 e to the power lambda 1 t. Now, let us assume that c1 is greater than 0. Okay. Then what will happen? When c1 be assumed as greater than 0, then these two equations give us b1 x equal to a1 by. Okay. So, the solution in the case c1 greater than 0, you can in this case b1 x equal to a1 by this gives you half line path. Okay. And since lambda 1 is negative, as t goes to infinity, okay, x goes to 0, by goes to 0. So, that means the half line path b1 x equal to a1 by enters 0 0 as t goes to infinity, and when we take c1 to be less than 0, we get the other half line path given by the line b1 x equal to a1 by. So, this solution x equal to c1 a1 e to power lambda 1 t by equal to c1 b1 e to power lambda 1 t represents two half line paths, okay, which approach and enter 0 0 as t goes to plus infinity, because lambda 1 is negative, and the line is given by b1 x equal to a1 by. So, they enter the 0 0 with the slope by equal to b1 upon a1 x, by equal to b1 upon a1. The slope of this line is b1 by a1. Now, if you take c1 equal to 0, then you get x equal to c2 a2 e to power lambda 2 t by equal to c2 b2 e to the power lambda 2 t. So, this also give two half line paths which are given by B2x equal to A2y. If you take C2 equal to 0, then the half line path is given by the line B2x equal to A2y, and if C2 is less than 0, then we get the other half line path given by the line B2x equal to A2y. But since lambda 2 is greater than 0 here, as t goes to minus infinity, x and y go to 0, x goes to 0, y goes to 0 as t goes to minus infinity. So, these two half line paths enter 0 0 as t goes to minus infinity. Now, let us take C1 not equal to 0, C2 not equal to 0. When C1 is not equal to 0, C2 not equal to 0, then what do we get? We have x equal to C1 A1. So, when C1 is not equal to 0, C2 is not equal to 0. Then these two paths represent these solutions 2 represents rectilinear paths, because as t goes to plus infinity, this part e to power lambda 1 t goes to 0, but e to power lambda 2 t part goes to infinity as lambda 2 is positive. Similarly, for the case the solution by e to power lambda 1 t goes to 0 as t goes to infinity, while e to power lambda 2 t goes to infinity as t goes to infinity. So, one part goes to 0 while the other part goes to infinity, and same is the situation when t goes to minus infinity. When t goes to minus infinity, e to power lambda 1 t goes to infinity, while e to power lambda 2 goes to lambda 2 t goes to 0. So, these two so the solutions 2 represent rectilinear paths and do not approach to 0 0 or as t goes to plus infinity or minus infinity. Let us look at y over x. So, y over x in this case is C1 B1 e to the power lambda 1 t plus C2 B2 e to the power lambda 2 t divided by C1 A1 e to the power lambda 1 t plus C2 A2 e to the power lambda 2 t. Let us divide these numerator and denominator by e to the power lambda 2 t. So, that we get C1 B1. First let us divide by C2. So, C1 B1 divided by C2, and then we divide by e to power lambda 2 t. So, what do we get? C1 B1 by C2 e to the power lambda 1 minus lambda 2 into t, and then plus B2, and this divided by, here we take also C1 A1 divided by C2, and then e to the power lambda 1 minus lambda 2 into t plus A2. So, as t goes to infinity, limit t goes to infinity. Now, since lambda 1 is less than lambda 2, lambda 1 minus lambda 2 t, lambda 1 minus lambda 2 is negative. So, as t goes to infinity, e to the power lambda 1 minus lambda 2 goes to 0, and therefore, y over x is equal to B2 by A2, and therefore, what we can say is that the rectilinear paths enter 0 0 with slope B2 by A2. So, we have, there are two half line paths, we can conclude now, there are two half line paths which approach and enter 0 0 as t goes to plus infinity, and two other half line paths which approach and enter 0 0 as t goes to minus infinity. This is in the case where we had taken C2 equal to 0, and this is in the case where we have taken C1 equal to 0. Now, all other paths are non-rectilinear paths. That means, when we have taken C1 non-zero and C2 non-zero, which do not approach 0 0 as t goes to plus infinity or t goes to minus infinity, but which become asymptotic to one or another of the 4 half line paths. So, this means that these non-rectilinear paths, okay, do not approach 0 0 as t goes to infinity. You see, this is what we have, y over x. Y over x is the slope of any point x y on the rectilinear path. This is B2 by A2. Okay. So, this means that the slope of the tangent to the rectilinear path approaches to B2 by A2, that is the slope of the line B2x equal to A2y. So, B2x equal to A2y, this line has the slope B2 by A2. So, non-rectilinear paths approach are become asymptotic to the rectilinear path B2x equal to A2y. So, they do not approach 0 0 as t goes to plus infinity or as t goes to, but which become asymptotic to one or another of the 4 half line paths as t goes to plus infinity or as t goes to minus infinity. Thus, the critical point 0 0 is a saddle point and it is unstable as shown in this figure. You can see here this is your half line path. As t goes to plus infinity, it goes to 0 0. So, it enters 0 0 as t goes to plus infinity, while this is another half line path, this one. As t goes to minus infinity, okay, it enters and approaches 0 0, but the directions are opposite. Here the directions are towards the point 0 0, while here they are away from the origin and away from 0 0. Now, these paths are non-rectilinear paths. These paths are non-rectilinear paths, and you can see that they become asymptotic to one of the 2 half line paths. These ones, these are asymptotic to this half line path, and these are asymptotic to this half line path. So, they become asymptotic to one of the 2 half line paths, and therefore, this point at origin is a saddle point, and these non-rectilinear paths do not approach 0 0 as t goes to plus infinity or minus infinity. Now, let us consider the example of dx by dt equal to x, dy by dt equal to minus by. So, here you can see a is equal to 1, b equal to 0, c equal to 0 and d equal to minus 1. So, what do we have? Lambda square minus a plus d. A plus d means 1 minus 1 is 0. So, 0 into lambda and then plus ad. Ad is minus 1 minus bc. Okay. So, lambda square minus 1 equal to 0, and therefore, lambda is equal to plus minus 1. So, the eigenvalues are lambda equal to 1 and minus 1. They are real, unequal and of opposite sign. So, we have case 2 here, and just as we have now seen, if the eigenvalues are real, unequal and of opposite sign, then the critical point 0 0 is a saddle point and it is unstable. So, this is the figure here. You can see here the 2 half line paths are, this is a half line path, this is another half line path, the other side of the half line path, and this is one half line path, this one, and this is another half line path, and these are non-rectilinear paths which become asymptotic to the 2 half line paths, this one and this one, as t goes to plus infinity or minus infinity. Now, here then 0 0 is a saddle point and it is unstable. Now, let us consider the case 3, where we will assume that the eigenvalues lambda 1 lambda 2 of the system are real and equal. So, let us say let the roots lambda 1 lambda 2 of the characteristic equation be real and equal, then we are going to show that the critical point 0 0 of the linear system is a node. So, let us begin with the situation where lambda 1 and lambda 2 are both equal to lambda and lambda is negative. So, we are assuming that both roots of the characteristic equation are equal, real, equal and are negative. So, first let us consider the case when a equal to d. Now, let us look at the characteristic equation. Characteristic equation is lambda square minus a plus d into lambda plus ad minus bc equal to 0. Okay. For the equal roots, we must have b square is equal to 4ac, okay, of a quadratic equation. So, that we can achieve in this case. In one case is this, that a is equal to d not equal to 0. Suppose I take a equal to d and not equal to 0 and bc equal to 0. Then what I will get? I will get lambda square minus 2a lambda plus a square equal to 0. And moreover, we shall have ad minus bc, which is equal to a square, and a is non-zero. So, ad minus bc is non-zero. Now, the two roots of this equation are a each. Okay. So, the characteristic equation lambda square minus a plus d into lambda plus ad minus bc equal to 0 becomes lambda square minus 2 ad 2a lambda plus a square equal to 0, and therefore lambda is equal to a and a is equal to d. So, the system of equations are dx by dt equal to ax plus by, dy by dt equal to cx plus dy. So, a is equal to lambda, so and b equal to 0, so I will get dx by dt equal to lambda x, and here c is equal to 0, d is equal to lambda, so we have dy by dt equal to lambda y, and we know how to find system the solution of general solution of an equation of the type dx by dt equal to lambda x. So, the solution is you can write dx by x equal to lambda dt, and then you integrate, you will get x equal to some constant c1 times e to the power lambda t, and similarly dy by dt equal to lambda y will give you other solution by equal to c2 e to the power lambda t. Now, you can see from here we have x equal to c1 lambda t, c1 x equal to c1 e raised to the power lambda t, and by equal to c2 e raised to the power lambda t. So, what we will get? We will get this equation c1y equal to c2x, okay. c1y is equal to c1 c2 e raised to the power lambda t, which is equal to c2x, okay. So, we will get this equation c1y equal to c2x. Now, the path defined by 5, defined by this 5, x equal to c1 e to the power lambda t by equal to c2 e to the power lambda t. For the various values of c1 c2 are half line paths of all possible slopes, and slopes will be, you can see slope will be if you take any point x y on the path, then the slope of the line joining the point x y to the origin will be y over x, which is equal to c2 by c1 c2 by c1, and so when c1 c2 are arbitrary, you can say that we will get half line paths of all possible slopes. Further, since lambda is less than 0, you can see here lambda is less than 0. So, as t goes to infinity, of these half line paths approaches and enters 0 0 as t goes to plus infinity, and therefore, we can say that the critical point is a node, and also it is asymptotically stable. If lambda is positive, we will have the same situation, we will have the same equation c1 by equal to c2x. So, we will have for various values of c1 c2 we will have half line paths, but because lambda is positive, these half lines paths will enter as 0 0 as t goes to minus infinity, and therefore, the point 0 0 is unstable, the node at 0 0 is unstable, and the arrows will be having opposite directions, all will be reversed. Such type of node we will call as a star shaped node. So, you can see this situation here, this is the case when we are taking lambda to be negative. So, all the it is a star shaped node where the directions are towards the center. If you take lambda to be positive, these directions of arrows will be opposite to the directions here. So, it is a star shaped figure, so we call it a star shaped node. Now, let us consider the other possibilities which will lead us to a double root, that means where the quadratic equation, the characteristic equation lambda square minus a plus d into lambda plus ad minus bc equal to 0 gives us a double root, okay. So, in that those possibilities let us consider now. So, in those possibilities, the general solution of the system we can write as x equal to c1 a e to the power lambda t c plus c2 a1 t plus a2 e to the power lambda t by equal to c1 b e to the power lambda t plus c2 b1 t plus b2 e to the power lambda t. Now, a's and b's here are definite constants, and they are such that b1 by a1 is equal to b by a, c1 c2 are arbitrary constants. Now, if you take c2 equal to 0 here, what you get from here x equal to c1 e to a e to the power lambda t by equal to c1 b e to the power lambda t. Okay. Now, then there are two half line paths which approach and enter 0 0 as t goes to infinity. We are taking lambda to be negative, we have taken that lambda 1 equal to lambda 2 and equal to lambda which is negative. So, x and y both approach to 0 as t goes to plus infinity, and if you take C1 equal to 0, we will get one half line path. If you take C1 less than 0, we will get the other half line path. Both these half line paths will approach to enter 0 0 as t goes to plus infinity. Okay. And when you consider the other case, so there are two half line paths which approach and enter 0 0 as t goes to infinity, and the slope is by over x. By over x means b over a. So with the slope b over a, if C2 is not equal to 0. Now let us consider the situation when C2 is not equal to 0. Then the general solution 2 represents non-rectilinear paths. If C2 is not equal to 0, then the general solution this represents non-rectilinear paths, and what we have, since lambda is negative, all these non-rectilinear paths satisfy the these equations. Limit of x as t tends to infinity is 0, limit of y as t tends to infinity. So all the non-rectilinear paths approach 0 0 as t goes to infinity. Further, if you find y over x, since C2 is non-zero, we can divide numerator and denominator by C2, and we get C1b over C2 plus B2 plus B1t equal to C1a over C2 plus A2 plus A1t. And when t goes to infinity, you can see here we can divide the numerator and denominator further by t, and so that C1b over C2t plus B2 over t plus B1, and here we will have C1a over C2. I mean to say this, when you divide, when you want to take the limit as t goes to infinity, you write y over x as C1b over C2t plus B2yt plus B1, and similarly in the denominator you write C1a divided by C2t plus A2 by t plus A1. So as t goes to infinity, we will have the limit equal to B1 by A1, which is equal to B by A. Hence all the rectilinear paths enter 0 0 with limiting slope B by A. Thus all the paths, both rectilinear and non-rectilinear, enter 0 0 as t goes to infinity with slope b by a. In the case of rectilinear paths also we have seen that the slope is b by a. Hence the critical point 0 0 is a node and it is asymptotically stable as shown in figure 3. In this figure you can see these are non-rectilinear paths. Okay. They are entering 0 0 with the slope of the line bx equal to a by. Slope of the line bx equal to a by is b over a. Okay. This gives you y equal to b over a into x, and you can see y equal to b over a into x becomes the tangent to these non-rectilinear paths while passing through the origin. So these non-rectilinear paths approach and enter 0 0 with slope b by a, and the slope of these half line paths is b by a. So this point 0 0 is a node and it is asymptotically stable. Now let us take an example on this. Suppose we consider dx by dt equal to minus x, dy by dt equal to minus y. Then the matrix A here is A, B, C, D. So this is equal to minus 1, 0, 0, minus 1. Okay. So determinant of A minus lambda I equal to 0 will give you minus 1 minus lambda 0 and 0 minus 1 minus lambda. So this implies lambda is equal to minus 1 minus 1. Okay. So the eigenvalues are real, okay, and equal. They have negative sign. So the critical point 0 0, as we have discussed right now, the critical point 0 0 is a node and it is asymptotically stable. And this is the figure. Okay. You can see the critical point 0 0 is a node and it is asymptotically stable. This is the case of a star shaped node. Okay. Here we have a star shaped node like in the case this one. This one we have a star shaped node, because for this star shaped node we had this assumption A equal to D not equal to 0, B equal to C equal to 0. If this is a special situation where we get a star shaped node, root in this case are equal, okay, root in the other cases that we discuss are also equal, but in this case we get a star shaped node and there we get a node which is not star shaped. So, here you can see the example which we have taken here, A is equal to D, A is equal to D is equal to minus 1, okay, and B equal to C equal to 0. So, we get a star shaped node. Okay. So, this node is a star shaped node and it is asymptotically stable. The figure is this one. Now, let us consider another example, dx by dt equal to x, dy by dt equal to y. So, here again we will get the matrix A equal to 1 0 0 1. Okay. So, this is unit matrix, the eigenvalues are 1 1. Okay. So, eigenvalues are lambda equal to 1 comma 1, they are real eigenvalues and they are equal. Okay. And in this case you can see again A is equal to D not equal to 0, A equal to D equal to 1 not equal to 0, and B and C are zeros. Okay. So, we get the critical point is a node, but remember here lambda is positive. Okay. Lambda is not negative, lambda is positive, the roots are real and equal. So, it is a node, but it is unstable. Now, we have compiled the information that we have so far regarding the eigenvalues lambda 1, lambda 2, the nature of the critical point depending on the eigenvalues and the stability of the critical point which can be inferred from the nature of the roots lambda 1 and lambda 2. So, let us summarize what we have done so far. So, if the eigenvalues lambda 1, lambda 2 of the characteristic equation or the matrix A are real, unequal and of the same sign, then the nature of the critical point of the linear system is a node. It is asymptotically stable if roots are negative. Okay. It is unstable if the roots are positive. Now, here if the eigenvalues lambda 1, lambda 2 are real, unequal and of opposite sign, then we have a saddle point and the stability of the critical point is unstable. Here we have when lambda 1, lambda 2 are real and equal, we will have a node. Okay. In the case where lambda is positive, okay, we will have a star shaped node, okay, while in the case where lambda is positive, okay, we will have unstable node. So, it is asymptotically stable if the roots are negative, a star shaped node, and asymptotically stable if the roots are negative, and again if the roots are positive, we will again have a node, but it will be unstable. So, with this I conclude my lecture. Thank you very much for your attention.